I've got a student here and a student on the phone. So my goal is to show you how to do it and also to explain well enough for the student on the phone to figure it out. All right, go for it.
A sealed balloon is filled with 1 liter of helium at 23 degrees Celsius.
Okay.
And then 1 atm.
1 atm, all right.
The balloon rises to a point in the atmosphere where the pressure is 220 torr.
220 torr.
And the temperature is negative 31 degrees Celsius.
Negative 31 degrees centigrade, right?
Yes.
Okay. And then what is it asking? What is the volume?
What is the change in volume of the balloons as it ascends from 1 atm to a pressure of 220 torr?
Okay, all right. So there might be a little bit of complication because what they're asking is not necessarily what is V2, but they're asking what is the change in volume. So the answer will probably end up being V2 minus V1. That's my initial thoughts as I hear this problem. Okay? Bradley, you got that?
Yeah.
All right, so here's the equation I want you to write down on your paper, Bradley. PV equals nRT. You got that one?
Yep.
All right, now solve for R. Get R all by itself on the right-hand side. And that basically means PV over NT is equal to R. We cool with that?
PV over MT equals R. Okay.
Yes. All right. Now, what I'm explaining to Andre is that the pressure, the volume, the moles, which is the N, and the T, the temperature, all can change. But the R is the same. The R is called the universal gas constant. It stays the same before and after. In the situation where it's like you have it at sea level, and in the situation where you have it at pressure equals 220 torr. Does that make sense?
Mm-hmm.
I mean, that's why it's called the universal gas constant. I can tell you exactly what it is. It's 0.08206 atmosphere liters per Kelvin mole, which is actually another big hint for us. We need to make sure to convert the temperatures all to Kelvin. So before I even start the problem, I want to do that. I want to convert everything over to atmospheres. I want to convert everything to liters. I want to convert everything to Kelvin, and I want to convert everything to moles. Does that make sense?
Yeah.
Okay. So in order to convert 23 degrees centigrade into Kelvin, I add, what was it, 273.65? Can't remember off the top of my head what that number is. Yeah, it's 273. Yeah. I think it's 273.15. So temperature 1 is actually, I don't want to write down 23 degrees centigrade. I want to write down, what is 23 plus 273?
So pressure is, so P, what is P? Is pressure,
well,
P1 is 1?
Right, because they said that they filled the balloon up at 1 atmosphere. So that's where the pressure was initially, right?
And the volume is 1 liter.
The volume was 1 liter, and the temperature is, what is 273 plus 23?
296.
296, all right. 296.15 Kelvin. That's your temperature initial, okay? Your temperature final, or your temperature 2, is, what is 273 minus 31? What is that? That's like 242?
242.
242, so it's like 241.85.
Now, why did you do that?
Because it's
subtract?
Well, it's because the final temperature is negative 31 degrees Celsius, so I need to add negative 31 degrees Celsius plus 273.15.
Oh, okay.
And so that's really just 273.15 minus 31, which is 241.85 or something like that. I don't have a calculator on me. I'm doing this off the top of my head. All right. There's one other piece that we need to do before we even start the problem, and that's convert the pressures to atmospheres. Now, for the pressure 1, we're good because we have 1 atmosphere. For the pressure 2, they gave it to us in torr, which is the same as mmHg. Is that correct?
I think so.
Yeah, I think so. So P2 is 220 torr, and then I'm going to multiply it by the fraction where I'm going to have 1 atm divided by 760 torr.
More.
because that's just converting it to atmospheres. We good? So I don't know. I can't do that in my head. What's 220 divided by 760?
0.289473684.
What?
28947
947 atmospheres.
3684.
Which kind of makes sense because it's rising up in the air, so the pressure is going to be less. When you go up in an airplane, there's less pressure. Yeah, 0.289 or something like that.
Yeah, 0.289. Okay.
All right.
And then
So I converted everything over to units that I want to use. Okay. Now here's the basic big thing behind the whole equation. You notice how you wrote down PV over NT equals R? Okay. If R is the same in situation 1 and in situation 2, then I could say P1 V1 over N1 T1 is equal to P2 V2 over N2 T2. Does that make sense to you?
Yeah. Yeah.
Okay. And that's really... Let me just write that down on the board. I know you can't see it, but I'm just writing down exactly what I told you. That's really the crux of what we're doing. I gave you the gas laws in 3 different forms. One's called Boyle's Law, Charles' Law, and Avogadro's Law. And it's really just saying like P1 V1 equals P2 V2, or I think it was V1 N1, V1 divided by N1 is equal to V2 over N2, and also V1 divided by T1 is equal to V2 over T2. But this law where it says PV over NT is equal to PV over NT, that's kind of combining all 3 of those ideas at one time. Does that make sense to you?
Mm-hmm.
Okay. Now we have to really think about it. We're asked to solve for V2. We're good there, right? The N1 and N2, are those different numbers?
No, they're both 1.
No, they're not both 1.
Wait, what did you say?
The N1 and N2.
Oh, N1 and N2.
N1, N as in Nancy, or N as in number of moles.
Are they both 1? There's 1 mole of...
Did I say that there was 1 mole in the problem? No. You can't assume that. So they're not. They're not 1, but I can tell you one thing for sure. They're the same. The number of moles inside the balloon at the beginning is equal to the number of moles inside the balloon at the end.
Yeah.
Because if they were different, what would that mean?
The balloon had a hole in it or something.
Some gas leaked out, right? And it didn't say that at all. Or if N2 were bigger, that means somehow helium got pumped into this situation, or whatever the gas is. You know, all of a sudden, when it goes up into the air, extra gas got into that balloon.
Yeah.
And that doesn't make sense at all. So as far as your PV over NT goes, you can actually cancel out the N's because they're the same number.
Okay.
Does that make sense?
Yeah.
So what do we need to solve for? We need to solve for V2, right?
V2.
So on my board, I have P1 V1 over T1 equals P2 V2 over T2. And I want to solve for V2. That's pretty simple. All I got to do is multiply up this T2 onto the left side, and divide out the P2 onto the left side. Does that make sense? This guy goes up, this guy goes down. So I have, and tell me if this is what you're writing down on your paper, Bradley, is P1 over P2 times T2 over T1 times V1 is equal to V2. I'll let you take a second to kind of digest that.
So can you repeat it?
All right. P1 over P2,
Yeah.
T2 over T1
Times V
times V1.
equals V2. Okay.
Yes. Now all you got to do is just plug in the numbers, whatever they may be.
Okay. So
Making sure, of course, now this is a big part, making sure, of course, to use your temperature as measured in Kelvin. So I know I gave it to you in Celsius, but you need to measure it in Kelvin. and also making sure to measure your pressure in the same units as the other one. Does that make sense?
So it's 296.15 times.
Actually, no. It would be 1 divided by 0.28947 times 241.85 divided by 296.15 times 1.
How did you get that?
Well, I got the 1 atmosphere from the P1. The P2 is 0.28947 atmospheres.
Oh yeah. Okay.
Right? That was our side work. Just on the side to make sure that before we even started the problem, we converted everything into the appropriate units.
I thought the first temperature was 296.15.
It is, but the first temperature goes in the denominator.
Oh, so it's not P2 over T, or it's not T1 over P2 anymore?
The answer that I got was P1 divided by P2.
T1 divided by P2, yeah?
P is in Paul.
Oh, P1 divided
Paul
by...
1 divided by Paul 2. Or I should just say pressure, because that's what it actually represents. Pressure 1 divided by pressure 2
and then
times temperature 2 divided by temperature 1.
Okay.
Do you understand why the temperature 2 is on top?
Yeah.
It's because it came from on the right side and multiplied it up.
Yeah. All right.
And then multiply that by volume 1.
Okay.
So you're right. So that 296.15, that's the T1 you talked about, that's going in the denominator of whatever your answer is.
Yeah.
The 241.85, that goes in the numerator.
Okay, so the first pressure was 1 divided by 2.89, then that times...
And I'll tell you one of the first mistakes that I bet you most people are going to make. A lot of people emailed me back and said, I've got such a poor grade on this homework, I don't understand what I'm doing wrong. I'll tell you what they're doing wrong, I can almost guarantee it. They didn't convert the Celsius to Kelvin. If you don't do that, all of this doesn't work. All temperature when dealing with gas has to be in Kelvin. So if I gave it to you in Fahrenheit, you would probably have to convert it from Fahrenheit to Celsius and then Celsius to Kelvin. Luckily for us, converting things from Celsius to Kelvin is actually pretty easy. You just add 273.15.
Mm-hmm.
All right? And then whatever your answer is there. I don't have a calculator on me, and I'm not supposed to be doing all of your homework for you. I just kind of gave you the principle behind it.